We're going to balance this using the algebraic method. First, start by adding variables A, B, C, D, and E because we have 5 chemical species. You're going to create linear equations for each atom type. The equal sign will show up where your yields or produces arrow is. There are 2 carbons associated with A and 1 associated with C. There are 3 hydrogens associated with A, 2 with D, and 1 with E. There are 2 oxygens associated with A, 2 with B, 1 with C, 1 with D, and none with E. The chlorines occur only with A and E. This shows us that A and E are equal to one another. You're going to select a variable, set it equal to 1, and solve for the rest. A was selected because it occurs in the most locations, telling us about C and B and D, as well as E, but also it has the highest coefficient of 3, allowing us to have reasonable answers when we get to the end, more manageable fractions if they evolve. When we solve, we find out that D is equal to When we solve, it turns out that B is equal to a half. We're not allowed to have halves, so we're going to go ahead and double every coefficient that we've created. Remember, with balancing, there are only really 2 rules. Have the same number of each atom type on each side, and have the simplest whole number ratio. The other method to solve for this would be the traditional trial and error, teeter-totter, seesaw method. Typically, to do this, it involves a RAP table. The reactants on the left, the atoms in a column in the center, and the products on the right. You'll then go ahead and count up each atom type and see which ones are balanced and which ones aren't. You'll then change the coefficients outside of each chemical species to try to get them to balance. Here, carbon and oxygen are our only real issues. Since oxygen occurs in multiple locations, it is unwise to try to balance it first. This is something that is learned. It is something that you have to remember. It is not something that's instinctive right away for most students. You'll then go about solving for the missing oxygen. But this assumes that a lot of these things are already set equal to 1, because if they weren't, then our 2 in front of the carbon monoxide couldn't be true. Once we do this, we could try to solve for the oxygen by itself. Doing this messes things up. So we start going ahead and trying to change everything, a little here, a little there. This is one that allows us to really see that the teeter-totter seesaw method has its limitations, especially as they become more challenging. We start crossing out things that we had already established, trying to make them work. It can become one of those things where you stop and you give up in the middle. Other times, you feel like you get success rather quickly. With the algebraic method, the only thoughts that you're having are those that are solve the math, follow the math. There's no if I do this, then that. The math just does itself. Next, I'm going to show how the RAP table and the linear equations are virtually the same thing. Realize that just because something occurs in more than one location, and the wrap table would add them all together, we can still see it in the linear equation, but we have to do that mental math. This is going to be true of the oxygens and the hydrogens in particular.